The nice thing about differential operators is that if you're using them to solve a system, you can work the system almost as if it were an algebraic system. Here, if I write this system using differential operators as dx dt, I could write as the derivative of x dx. And dy dt, I'm going to write as the derivative of y. So I get dx plus dy is equal to e to the t. On this second equation, I get negative d squared x, because I have the second derivative of x. And then I have another derivative of x plus dx, and then plus x plus y is equal to 0. Now, you can solve these systems algebraically. You could solve them either by elimination or you can solve them by substitution. Because this equation is real easy to solve for y, I'm just going to solve by substitution. If I bring the y over to the right side, that's going to give me a negative y. So to get y, I'm going to have to multiply through by a negative. That's going to change this to a plus, to a minus, to a minus. And I'm going to get y equals negative d squared x plus dx. No, that should be a minus. Minus dx minus x. And I'm going to write this that changes to a plus and a minus. I'm going to write this by factoring out the x as d squared minus d minus 1 times x. And then I'm going to make a substitution into this first equation. So this first equation, which says dx plus dy equals e to the t, becomes dx plus dy, and y is d squared minus d minus 1 applied to x equals e to the t. Now notice here I could apply the differential operator just like you would distribute. So I get dx plus d to the third minus d squared minus d, all applied to x, equals e to the t. And we could work this almost as if it were a polynomial, and we could add these like terms. Dx and negative dx cancel each other out, so that I'm left with d to the third minus d squared applied to x equals e to the t. Now, what I would like to do is solve this equation so that I completely annihilate everything, including this e to the t. This e to the t can be annihilated by applying a d minus 1 to both sides. And then I get d minus 1 times, I'm going to factor this out, I'm going to factor out a d squared, and that leaves me with another d minus 1 is equal to 0. I could write that as d squared times d minus 1 squared equals 0. Oops, applied to x, applied to x. And now what I want is I want to find my polynomial that will make this true. what polynomial is annihilated by these differential operators? Well, a d squared will annihilate a polynomial, first degree polynomial. So it'll annihilate something in the form of at plus b, first degree term and 0 degree term. D minus 1 squared, a d minus 1, just like here, annihilates e to the t. Whoops, not a. I have to use a different letter. C e to the t. And because I square it, it also will annihilate a t e to the t term. So here's my solution for x. And then once I know what x is, I can easily go and find what y is. Y is d squared minus d minus 1 applied to x. So y is my second derivative of at plus b plus c e to the t plus dt e to the t minus my first derivative of that same function minus that same function. So when I calculate this out, I'm going to start by doing my first derivative of this function. That's going to give me an a. The derivative of b drops out. Derivative of c e to the t is c e to the t. The derivative of dt e to the t, I need to use product rule, is going to give me d e to the t plus dt e to the t. And then minus the derivative of that same function gives me what I have in parentheses here, a plus c e to the t plus d e to the t plus dt e to the t minus at plus b plus c e to the t plus dt e to the t. Okay, now all on this time when I take the derivative, I'm going to line up my like terms so I can add them all together. The derivative of everything I have inside this first parenthesis, that'll cancel out the a. That'll give me a c e to the t plus d e to the t. And here I need to use product rule. I'm going to get d e to the t, it gives me two of those, plus dt e to the t. And then subtracting all of this, I've got a minus a minus c e to the t, goes here, minus d e to the t minus dt e to the t, and then subtract off at, go over here, subtract off b, that's a constant, I'm going to line it up with this constant, minus c e to the t minus minus dt e to the t. And that gives me y is equal to, these two cancel, I'm left with negative c e to the t. 2 minus 1 gives me a plus d e to the t. These two cancel, I get minus dt e to the t minus a minus b minus at. This is my constant term. These are also like terms. But there's my y for solving this system. There are other ways to solve systems of equations. Using this differential operator is one way. You could also have solved this differential equation. You could have solved this differential equation by rewriting it in terms of derivatives. X prime plus x triple prime minus x double prime minus x prime is equal to e to the t. You could have solved that as a higher order linear differential equation. That's with constant coefficients.